In this next unit, we're going to be looking at the reduction of multiple subsystems. So a good question to ask is, why do we even want to bother with being able to reduce multiple subsystems? Well, of course, as you might imagine, most practical systems are going to be rather complicated and they aren't just going to have a single transfer function. So our goal here is to basically reduce these more complicated systems to a single transfer function. So we want to reduce to some single transfer function, G of S, T of S, whatever we're going to call it. So single transfer function. And the benefit of doing that is once we have this as a single transfer function, we can then use our equations from the previous unit. So we can use equations from our time response material. And so from that, we can determine the type of response. If the system happens to be underdamped, of course, we can then go on to talk about the peak time, percent overshoot, all of those other characteristics that we talked about in the previous unit. So it turns out we're going to look at two different ways that we can reduce subsystems. So we're going to look at two general methods. And so the first of those two methods is just going to be using block diagrams. And so we've kind of been using block diagrams without sort of addressing a lot of the sort of little details of it. So we're going to come back and in the next couple of videos, we're going to talk about everything in detail about our block diagrams, how we can manipulate them, and ultimately how we can use them to reduce our more complex systems. So we can use this in our frequency or the time domain, but typically we're going to use this in the frequency domain. And so that works out because that's, of course, what we've been studying so far. So typically used in our frequency domain. And so what we're going to do, and we'll see this in later videos, is we're going to be utilizing block diagram algebra. And so we're going to be utilizing that to reduce our system. And again, keep in mind, our goal here with this block diagram algebra is ultimately we want to have a single transfer function. So that's the first of our two methods. The second is going to be using something called signal flow graphs. And signal flow graphs are typically going to be used in something called state space. And so we've actually sort of skipped over that. If we have time at the end of the semester, we're going to come back and talk about this. But typically used for state space analysis. And so we can think of state space as sort of just being another sort of option as opposed to doing analysis in the frequency domain. So again, we'll come back to this if we have time. And what we're going to see if we're working with these signal flow graphs, we're going to use something called Mason's rule to reduce our systems. And what we're going to see later on is that there is actually a way that we can convert back and forth between our block diagrams and our signal flow graph. So maybe you're given a particular system in one format. It's not that complicated to switch it to the other if you're more comfortable with that, or if maybe the situation dictates that that's what should be done. And no, really either of these methods work in both the frequency and the state space. I've just mentioned here that typically block diagrams are used more in frequency domain, whereas typically the signal flow is with state space. And again, both of these methods can be used to analyze the system, or they can be helpful as we're designing a system.